Here we go, fourth quarter of OChem. That's right, we had the first two quarters in 12A, and now we're in the second half of 12B, so fourth quarter. Let's do this. This weekend was my wife's birthday, so Oma made lasagna, and Michaela made these incredible desserts, these cupcakes, so good. And she made a chocolate ganache raspberry chocolate cake with a raspberry cream filling. And so today we got announcements, and then we'll do chapter 16, electrophilic aromatic substitution. So we do have the exam coming up Wednesday. I got the details in the next slides. We're not quite doing total synthesis yet. I'm meaning to get that going, but we'll get there. And spring break after this week, so let's push hard. Let's study well for exam 2, and then take a little break. So exam 2 details. So the exam is going to be over chapter 12, but just the last, it'll focus on the last two outcomes, the osmium tetroxide dihydroxylation and the ozonolysis reactions. I won't go crazy with those, but those weren't on exam 1, so they'll be on exam 2. And then chapter 16, well, after 12, we'll have 13, 14, 15, and then 16, but only outcomes 1 and 2 from 16. And I'll be talking about that today. It shouldn't be a problem. It's just going into the electron withdrawing and donating effects on acids, something you've seen before. Okay, I'll email you all the exam at 9:30 a.m. Wednesday, April 1st, 2020. No joke, I know it's April Fool's Day, but that's when we have our exam 2. So you should get that email then, and then once you get it, you'll need to complete it and email it back to me by 3 p.m. So that's a 6-hour window on the same day. No joke again. And you can print out the exam and handwrite your work and then scan it in and upload it to Canvas. Or you can, if you have a tablet, you can, if you feel comfortable, you can write on the tablet file and then upload it to Canvas when you're done. And or you can handwrite out the problems on a blank pieces of paper if you don't have a printer, and then upload it to Canvas. Try to upload a single file. I know for me, I can do it with my Cam Scanner app. I scan the pictures as batches of the batch, and then I save it as I email it to myself as a PDF, which then you can email to me. There's other ways to do it too. There's like, you can use the Notes app in your iPhone if you have an iPhone, and there's Adobe. There's a lot of different things, so try them out. And then on our Canvas website, upload your exam to assignments, exams, exam 2. So, and then I consider if you ask a friend for help during the exam, or use notes during the exam, or use the internet during the exam, is cheating. And I know it's like crazy times, but let's see if we can do this right. Stay clean. Using anything other than what I give you on the exam is cheating. So I'll put a periodic table in the exam. And just do your best. Let's show me how much you're learning. And if you have any questions during the exam, email me. I'll be there by my email, ready to answer those. I listed my office hour as different times in different places. Sorry about that, but here are the actual office hours. So Monday, Wednesday, 11 to 2 p.m. So I'll have the exam. I'll have the lecture on YouTube already, and then I'll be Zooming from that time, 11 to 2, to help questions. And then Tuesday, Thursday from 9:30 to 10:30 a.m. I have an office hour. And then this was the time that I had listed differently. I had it as 1:30. This doesn't make sense. No, this is it. I had it 11:30 to 12:30. And no, it's actually 12:30 to 1:30. And then I'll have bonus office hours sometimes. Like I had one today, Sunday. But I post all these office hours online under office hour questions on our website. So if you miss an office hour, there's a lot of good practice problems explained in detail there. That's a great resource for you now. So after exam 1, I had given you some advice, and I want to give it again. So the advice was practice the mechanisms a lot every day. Even the old mechanisms, try working them out for about 10 minutes. And every time you practice the mechanism, it makes you better at all mechanisms, not just that one. And then from now on, I want you to always show all your electrons, lone pairs, and things like that. And I did a little animated mechanism. I did an animated PowerPoint slide of this. I'll show you that now again. So here's some common mechanism errors that I consider errors. Say we're going to protonate this alcohol, make it from a bad leaving group into a good leaving group, and we just leave off the dihydrogen phosphate. That's not good. I might take points for that. Then let's say you just dry up the dihydrogen phosphate like that. That's pretty good, but I still don't like it as much as if you show the fact that this oxygen had 2 lone pairs. Now it has 3 from the 2 electrons from the bond. Let's draw that all out. But there's one thing I don't like about this. I don't like the bond being showed between oxygen and hydrogen. That's weird. So let's do this. Oxygen to phosphorus. You can abbreviate this parts, but let's keep all this clean here where the reaction took place. So that looks good. And then another error is that, let's say you form a carbocation with that good leaving group, and then you just stop there. That's not so good. I want to see the water that came off too. I want to see everything in the reactant side that changed over here in the product side. So does this look good? Not the best, because I have a lone pair, one lone pair, and I just gained another one. I want to see that evidence of that. So let's do that. Let's go. Boom. There we go. Both lone pairs. Now it's good. Okay, our virtual SO2W is at Grizzly Granite Bay High Grad, or Granite Bay University. A bio major, will specialize in neuroscience. Loves to roller skate and ice skate. I wonder if they play hockey sometimes. Has been taking ballet for about 4 years. First position, second position, on your toes. Notorious for having untied shoelaces. I wonder if that works out with ballet. And a milk person, not tea or coffee, so no. Skip the tea or coffee, just give her milk. Oh, I gave something away. Likes to apply special effects makeup on Halloween. Has never used a vending machine. This was my favorite fact. Never used a vending machine. That's pretty interesting. And here it is. Who's that? Our first ever zombie SO2W. That's right. It's not Jealous Sam. It's not Jealous Sharon. It's Nishida Fernandez. Let's give her a Sierra College warm welcome. Next, I want to talk about major resonance, deciding what's the major resonance structure when you have resonance. This will be a big part of chapter 16. So here we have a reaction between an amide and an organolithium. The organolithium is an extremely strong base, but it's also a nucleophile for carbonyls. So is it going to attack the carbonyl? No, it'll just deprotonate the amide because acid-base chemistry dominates it. It's such a strong base. So I can make that amide, which has resonance, and the butane bastard gas. So looking at these two resonance structures, which one's the major resonance structure? Oh, before I do that, the pKa of an amide is actually 17. It's pretty low because the conjugate base is stabilized by resonance. And the alkane that's produced, pK is 50, so this is very product favored. So now back to deciding what's the major resonance structure. Oxygen is more electronegative than nitrogen, so it'll prefer to have the negative charge. So this will be your major resonance structure. Also, I didn't mention it, but all the atoms that want octets have octets in both resonance structures. So here would be our resonance hybrid. The oxygen would have, we would expect more negative charge since it's more electronegative. All right, what about this one? What about this nitrogen protonation? So do we expect this to happen most of the time where we protonate the nitrogen and this conjugate acid has no resonance? If I tried to do that, it would break the octet rule for nitrogen, so it's just that. Or should we consider the oxygen being the base? So if we protonate the oxygen, we make a conjugate base that looks like this, and when you look at the resonance of it, you get a resonance structure. So this conjugate acid is a lot more stable than that one. So the more stable conjugate acid, the stronger conjugate base. So it turns out that oxygen is more basic and nucleophilic than the nitrogen, or this nitrogen. And now between these two, what's the major resonance structure? It has resonance. And what's the major resonance structure? That's the major resonance structure. Why is that? The nitrogen has a positive charge and it's less electronegative. It can handle it better. The oxygen is more electronegative. It doesn't want a positive charge. And so the resonance hybrid might look like this. More positive charge on the nitrogen, less on the oxygen. One last example. Here we have a carbocation with an oxygen attached to it. So you can see resonance like that. So who's more electronegative? We know oxygen's more electronegative than carbon. And what is going to be the major resonance structure? Do you think it's going to be the one with the carbon, the least electronegative with the plus charge, or the more electronegative oxygen with the plus charge? It's going to be this one. So that might seem wrong because you're thinking oxygen's more electronegative. It wants to pull electrons to it. Why would it want to be positive over the carbon? The reason why, all octets. This resonance structure, that carbon has an octet, the oxygen has an octet, 2, 4, 6, 8. But over here, that carbon doesn't have an octet, 2, 4, 6. The oxygen still does, 2, 4, 6, 8. So when you have a resonance structure with all octets, we usually say that's the major resonance structure. So octet considerations override electronegativity considerations. Okay, let's talk about p orbitals. I found these awesome pictures online. I think you're going to like these. These are these nice animated, like shiny p orbitals, p atomic orbitals. So here is a 2p atomic orbital. We got the one that's in the plane on the x-axis, the other one in the plane on the z-axis, and then the y-axis. That's the one that's coming right at us. That's the one I draw at an angle. So these p orbitals are the p orbitals that carbon has, nitrogen has, and oxygen has, because they're in that same row of the periodic table. Next up, and notice there's just one node for a p orbital that we've been drawing that all along. There's 0 probability of an electron being found between these two lobes, but somehow an electron can beam across. Pretty interesting. Now look at the 3p atomic orbitals. I don't know if you knew, but they got extra nodes. Isn't that cool? So sulfur has a 3p orbital like this. Chlorine does. And so because of their makeup, they have 1 and then 2, 3 nodes. Pretty cool, huh? And they're larger than the 2p's. And then 4p atomic orbitals, like bromine has, have 5 nodes. 1, 2, 3, 4, 5. Pretty crazy, huh? I like the way they look with the shine on them. And then 5p atomic orbitals, they have 7 nodes. I have a cool little video of this. Let's look at it. So here's our 5p atomic orbital. Oh, isn't that sweet? So we've got 1, 2, 3, 4, 5, 6, 7 nodes. I like the way it looks right here. Let's see, I'll show you. 1, 2, stop. Oh, and back it up a tad. See right here? So the way it's being drawn, there's a little gap between there. So that's the node, and so what it's saying is there's 0% probability an electron could be between these two, but somehow there's a probability of an electron being here and the same electron being there. So it can beam across. 6p atomic orbitals, they have 9 nodes. Let's look at those. Here it is, the 6p. Super cool, huh? You see 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes. Awesome, huh? So what was the point of showing you these p orbitals? It has to do with their pi bonding. So let's look at, for example, carbon to bromine pi bonding. So the reason why I bring this up is we'll see examples like this soon. Bromobenzene. It's a single bonded to a carbon, but it can have resonance, and it's got a little bit of double pi bonding occurring between the bromine and the carbon. I know this is a separation of charge, but it's still a little bit a part of the nature of bromobenzene. So let's look in more detail at that pi bond. So this can represent, these are drawn to scale too, these 2 p orbitals. So this is a atomic radius of a bromine is a 4p orbital, is 94 picometers. So here's your bromine p orbital, like this bromine, and then here's your carbon p orbital, this carbon say. It's said to be about 67 picometers. So they're different sizes. And do they overlap well? Well, I can see this gold and this gold are in phase. They would overlap. But the red part here is going to antibond with the gold. That's going to like repulse. But then that little bit of gold will try to get in there. And then on the other hand, the red and red overlap, but then the gold is messed up. And then the red and red. So you can see it's not going to be the strongest pi bonding because the p atomic orbitals don't match up in size. This is bigger and that's smaller. And also, so that leads to weak resonance. Also, the p atomic orbital nodes don't match up well. So the pi bonding, it does occur between bromine and carbon. It is important, but it's not as strong as other pi bonding. And I have another slide here. I made this up as part of the extra credit for chapter 16, the England absence thing. I said it's extra credit, but it should be required. So I'm going to say it's required extra credit. So everybody's got to do this. If you don't do it before exam 2 on Wednesday, you're okay, because that material is not going to be on the exam. But it is, in a way, like it's electrophilic aromatic substitution, but just in details that you won't get a question for on exam 2. Definitely will on exam 3. But if you do it before exam 2, it's going to really help you for exam 2. So here's what I'm talking about. A carbon and an oxygen, they pi bond well because they both use 2p atomic orbitals, same number of nodes, about the same size, so their bonding is in phase, in phase. So you get good overlap between the 2p to 2p atomic orbitals, whereas a carbon and chlorine, they don't pi bond as well because the chlorine's got a bigger 3p atomic orbital, carbon's got the smaller 2p, and chlorine's got these extra little nodes. So there's bonding here between the carbon and the chlorine p orbitals, and it's out of phase here, so it's a little bit anti-bonding, anti-bonding, bonding. And I tried to represent this as best I could. I think this is a good, I've seen this kind of representation a lot for a pi bond. So that's pi bonding above and below when these p orbitals are in phase. This would be your lowest energy molecular orbital, the bonding one. Now when I go to this one, this is my best representation. What do you think? I'm trying to show that the carbon p orbital is smaller and the chlorine's bigger, and they do overlap above, but then this part of the carbon's p orbital is repulsed by the out of phase part of the chlorine's p, so it's pushing out. But overall, what I want you to get from this image is that carbon and oxygen have very strong pi bonding, where carbon to chlorine is weaker. Okay, and then lastly, we can chlorinate a benzene ring with chlorine and iron 3 chloride. There we go. Brominate with bromine and iron 3 bromine. Nitrate with nitric acid and sulfuric acid. And we can sulfonate with a fuming sulfuric acid, the SO3 gas. And this is reversible. I'm going to actually start lecture off. I'll show you that mechanism, the reverse. If you add water and heat. So this is concentrated sulfuric acid, not much water or any at all. But now we're going to have plenty of water. It's going to reverse the reaction. And then we got Friedel-Crafts alkylation or acylation. Bam, there we go. And then Friedel-Crafts alkylation. That's it. Oh, I got a whole mechanism for you here. You ready? You can tell this was from like a couple years ago, and now I've been getting better at this stuff. So this is nice for you guys. We're going to do the bromination mechanism. So the aromatic ring is very weak. It's a very weak aromatic nucleophile. So, and the bromine's a weaker electrophile. So we have to first start with Br2, the weaker electrophile, and add iron 3 bromide as a catalyst. And look at that. It does a Lewis base, Lewis acid, lone pair donor, lone pair acceptor reaction. And now we get to this point, and that is the super electrophile. Look at that. I made it super. And now the very weak aromatic nucleophile can react because this is super. And it's going to go to the N bromine, not the middle. It's going to break that bond. There we go. And we get a carbocation. This carbocation has resonance, and that's important. We did lose aromaticity, but at least we have a little bit of resonance to stabilize this. There we go. And then to finish off the reaction, oh, well, before we do that, I'm going to show you you could think of the resonance hybrid here, plus on that carbon, plus on that one, and then that one, right? So you got, and then it's a plus charge shared over all three, so we could say it's about plus a third at the ortho positions and plus a third at the para position. And plus charge on ortho para, not meta. It's interesting, huh, how it skips those. And then this is referred to as the ipso carbon, the carbon with the bromine, and those two are the ortho, meta, and para. And then to finish off the reaction, we need to re-aromatize. So we're going to deprotonate the carbon that has the bromine added to it. So it makes room for the bromine to be the only thing on there. And I did it from this resonance structure, but I could draw from all of them. And when I draw from that one, I get that product and I HBr and my iron 3 bromide catalyst back. And it is pretty weird to see HBr produced. It's such a strong acid. But these are extreme conditions with super electrophiles. I mean, it's not every day that your electrophile can fly, you know, so it's just different conditions. All right, catalyst regenerated. And I could show for these other ones too for fun. There it is. That would give you the product, right? Or I could show it for this one. You can draw for any of the resonance structures to get there. So we made the super electrophile. Dun, 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 dun. We lost aromaticity, step 2. And this is no longer aromatic because this carbon is sp3 hybridized. It's not sp2 all around the ring, so this is neither aromatic or anti-aromatic. And 3, we re-aromatized, boom, deprotonated that. So now it's sp2, 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 flat ring, 2, 4, 6 pi electrons, aromatic. Let's start the review off with some old alkene reactions. Not too old, but here we have a alkene with Br2. What's going to happen with that? You're going to get the anti-addition. In this case, you get enantiomers. They look similar, but they won't overlap, even if you spin them around. And they're mirror images, so they're enantiomers. And next up, ozonolysis. So ozonolysis has lyse in the name, like a lysosome. It's a protein that cuts things. Ozonolysis, ozone cutting things. So it's going to cut right through there. It's going to make a ketone on this side and an aldehyde down there with this hydrogen sulfide reductive workup. So we got the aldehyde on this end, ketone there. And then hydroboration, that's even further back, but we could do that one. Just got to remember it's syn addition, anti-Markovnikov. Syn OH and the H are on the same face. Syn addition, anti-Markovnikov, not anti-addition. And then dihydroxylation, that's one from the end of 12 that wasn't on chapter 1, so it'll be on chapter, it wasn't on exam 1, so it'll be on exam 2. So here we have osmium tetroxide with a reductive workup, zinc, and this one goes about by syn addition. So the OHs, 2 alcohols, are syn, so they're both wedged or both dashed. And this carbon's not a stereocenter, a methyl-methyl. It doesn't matter how you draw this one, but this one's a stereocenter, so you have to draw these 2 enantiomers.
Whatever it is, I think I see becomes a tootsie roll to me.
Another thing I'll show you is how we put bromine on things, alkenes. Put bromines on a lot of things, so everything I think I see becomes a bromide to me. It's the old Tootsie Roll commercial. So here we go. We got bromine and light. We could put secondary bromide to be the major product. Alcohol, can we make that into bromine? Bromine, yes. You can add PBr3 or HBr. There you go. And then what about an alkene? Can an alkene react with bromine? Add some bromine atoms? It sure can. Br2, carbon tetrachloride, gives you the anti-addition, which in this case you can abbreviate since the N carbon isn't a stereocenter, and that's anti-addition. And then what about MBS and light? Carbon tetrachloride, that one. The MBS creates a very low, steady concentration of Br2. The light breaks it up. You get a radical bromination, allylic bromination. And then when you add HBr and hydrogen peroxide, you can get anti-Markovnikov hydrobromination. Then when you add HBr alone, you can get the Markovnikov hydrobromination. Okay, now for some alkyne reaction review. So if you start with a terminal alkyne like this, or internal, and you add Lindlar's catalyst, which is down there, but all right, let's do some alkyne reaction review. So if I have a terminal alkyne like this, and I treat it with hydrogen gas or deuterium gas, I can do a partial reduction of the alkyne, just reduce 1 pi bond if I use Lindlar's catalyst, all of this down here. So this has palladium metal on calcium carbonate, similar to palladium metal on graphite or carbon that we've talked about for alkenes. But then you add in some lead, 2-acetate, and quinoline, and these poison the catalyst, so it only reduces partially. And does it give syn or anti-addition? It gives syn addition. So the two deuteriums are on the same side. If it was hydrogens, they would be on the same side. And then we could also do sodium metal reduction. This is where you have sodium metal and dissolved in ammonia, liquid ammonia. This particular liquid ammonia is deuterated, and we use D2O workup. And what you wind up with in that one, anti-addition. So if you want syn addition, use Lindlar's catalyst, anti-addition, dissolving metal reduction. All right, what if we add mercury 2 sulfate and acid to this guy? We initially get an enol in the middle carbon, and that tautomerizes to the ketone. So it's a Markovnikov. Oh, and then what about when we use this big dicyclohexylborane? You'll initially get an enol on this end, of the terminal end of the alkene, which tautomerizes to the aldehyde. So you got Markovnikov, anti-Markovnikov. All right, I got some review stuff for us. Let's get ready for this exam. So this is an animation that's on our website. Well, it's not animated on our website, but the reactions are. This is from the mechanism database, chapter 13. So let's look at the first reaction. If you have a terminal alkyne, you add an organolithium, what's going to happen? Deprotonate it, make an alkyne anion. And these alkyne anions can do all kinds of reactions. They can react with epoxides. So here, this is my second thing I'm going to look at. And how does it want to react with the epoxide? Does it want to hit the less hindered or the more hindered? It's going to go mostly to the less hindered. No stereocenter there, so this looks correct. Then next up, what if it reacts with an aldehyde? It just adds like it's a organolithium or a grignard. It's nice, right? And then next up, let's look over here now. A methyl bromide, what can happen with that? SN2, it can come right back in there. Boom. This is a very strong base, but a methyl bromide can only do SN2. And then a bromoethane, primary electrophile. Let's see. SN2 again, kicks out the bromine. And now what about a secondary electrophile? It's getting more crowded here. The cone of reactivity got a lot smaller. Oh, looks like we did E2 major. So this hydrogen off of this end got deprotonated. Tink, tink, tink. E2, you make the alkyne back. So let's just reiterate those SN2s. So for the secondary electrophile, this one, it's just too much steric hindrance for the strong base / nucleophile, the alkyne anion. So E2 is major. But for the methyl electrophile, it has like the least amount of steric hindrance. So that one can do SN2 major. And the primary as well. As long as it's not branched, it should do SN2 major. It's nice. Here's a little more. We could talk about allylic resonance and the pKa of an allylic carbon. So the allylic carbon is more acidic than a normal alkane. Its pKa is about 40. So a strong base like N-butyllithium can deprotonate that. And the reason why this is fairly acidic is because the conjugate base has resonance. And the pKa of the acid that's formed is 50, so that butane bastard gas is a weaker acid than the starting acid, and so it's a product favored reaction. And we can see there's resonance for allylic radicals as well. Practice those, and for carbocations. And we learned about allylic bromination, where NBS here generates a very low concentration of Br2, so it won't do the di-addition, the anti-addition. Instead, it gets hit with light, radicalized, makes this allylic radical that then winds up making the allylic bromine. All right, we got some DielsAlder review here. So diene focus. So if the diene has its methyls out and out, then they wind up being cis, like that. If you have one methyl out and one methyl in, they're trans. So in this case, you'll get enantiomers. They almost look alike, but they're not. All right, now let's focus on the diene. Cis-diene, cis-dienophile. Cis product, sorry. Trans-diene, trans product. You get diastereomers in this case. Then DielsAlder, if you have a diene that's in a ring, you're going to get a bicyclic, and these two are cis, so they'll be cis still. So there it is, the indo and the exo products, and that's the major product, the indo. And then the electrocyclic reactions, if you work out this whole thing, you can use light. In this case, it gives you the cis product, and heat gives you the trans. I did a lot of examples like this on the office hours questions if you want to review that. So does heat always produce trans? Does light always produce cis? No. So for instance, see how this alkene here is trans and that alkene is trans. What if I have the bottom one still trans and the upper one cis? That's going to change it. Now heat is going to give me, or light's going to give me the trans products, and heat's going to give me the cis. So switching one of those switches the result. So heat gave me trans, and now heat gave me cis. So there's 3 factors in these, as I've said before. There's the number of pi bonds. This has 2, but you could have 3 or 4. That affects it. And then heat or light's another factor. And then the stereochem of these alkenes here affects it. Here's a nice triene example. Got the mechanism for you too. So heat winds up giving you the cis product in this one, and light gives you that. And review looking at the molecular orbital diagrams and the outer orbitals for that. Oh, the molecular orbital diagrams, that would be a good one too. I'll probably ask you that on the exam, how to fill out a molecular orbital diagram. And then notice how you went from 3 pi bonds to just 2. So if you're doing a retro and you see a diene like this, you could think, oh, that came from electrocyclic. And then, yeah, you get the 3 pi bonds, they rearrange in a way that you make 1 new bond and get 2 pi bonds still. Yeah, draw your molecular orbital diagrams to confirm those products. And then aromaticity, quick review. So to be aromatic, you need to have a flat ring, sp2 all the way around, and you need to have a certain number of pi electrons that can be generated by this formula. I put 0 in there. 2 pi electrons, 4, 6, no, 2, that's 4. To be aromatic, you get 2, 6, 10. To be anti-aromatic, you have to be a flat ring, sp2 all the way around, and have a different number of electrons. So it could be 4, 8, 12. But a ring, if it can, it prefers neither if possible. To not be anti-aromatic, it would rather be neither. So to do that, it can like stretch out its bond, not be flat, change one of the atoms to be sp3.